Yo, what's up everyone? Welcome back to Thermodynamics. Today we're going to be talking about enthalpy. So let's start by defining what enthalpy is. Enthalpy is all the energy in a system. So this is going to be all the internal energy that a system has, and it's also the energy required for that system to exist in space. There is a little bit of energy associated with the space that the system takes up, so we have to add that also into enthalpy. Now, using this, we can kind of set the definition that enthalpy is equal to E, which is the internal energy, plus PV. PV is pressure times volume, and that represents the energy required to have that system exist in space. The problem with this is that we can't really measure enthalpy. If we went to go find all the internal energy, there's just way too many places for energy to be within that molecule. It's kind of like if you wanted to measure all the water in all the oceans. There is just way too many places for water to be. That's why we can't really measure enthalpy. However, we can measure change in enthalpy. And that's what we're going to be dealing with. And in specific, under constant pressure, your change in enthalpy is going to be your heat of reaction. And that's going to be a really important factor that allows us to do a lot of things with enthalpy. Your change in enthalpy is always relative to the system. So if your change in enthalpy was negative, then that means your products have less energy than the reactants. Those types of reactions are what we call exothermic. On the other hand, if your change in enthalpy was positive, then that means your products have more energy than your reactants, and we call those types of reactions endothermic. So if your delta H was negative 890.1 kilojoules per mole, that would be exothermic. But if it was 73.8 kilojoules per mole, that would be endothermic. So we're going to go through a couple types of enthalpies. There's a couple types of enthalpies. They all represent really the same thing, but we give them different names. So let's start with enthalpy of reaction. Enthalpy of reaction is the heat energy absorbed or released by a chemical reaction at constant pressure. It's also sometimes called the heat of reaction, and that's what you're going to see it written as a lot of the time. So if you look at a reaction like CH3OH reacting with oxygen to produce carbon dioxide and water, your heat of reaction is negative 677 kilojoules per mole. Then that means your products have 667 kilojoules per mole of energy less than your reactants. This type of reaction is exothermic, and if you look at a different reaction where your heat of reaction is positive, that would be called endothermic. Although we now know the difference in energy between the products and the reactants as told by our heat of reaction, we don't actually know how the potential energy of our system changes over time. The heat of reaction tells us that in this case, we are dealing with an exothermic reaction. This is exothermic because our delta H value is negative. This means that if our reactants started over here, this is our reaction coordinate, by the way. Our reaction coordinate represents the reaction over time. So at the start of the reaction coordinate, you have all reactants. And all the reactants, let's say, are at this potential energy. In this reaction, our products would be at a lower potential energy than our reactants. So at the end, let's say we have all our products, and this would be at a lower energy. This is because our reaction is exothermic, meaning our products have less energy than our reactants. So how do we connect the reactants and the products? You'll see them being drawn like this. This is how the potential energy changes over time. Over here is our transition state, and we'll learn later specifically what this is, but the difference between this top energy level and our reactants is what we call the activation energy. It's represented by EA, and the other value, the reactants to the products, is our delta H. And this is how it looks for an exothermic reaction. So our reactants are above our products, but it would look a bit differently for an endothermic reaction, for something like this. In an endothermic reaction, let's say your reactants start over here, and at the end, when you have all your products are going to have more energy than your reactants. So it's going to be at a higher level than our reactants. What doesn't change though is the general shape that your graph takes. And your graph still has this transition state, and the difference between that and your reactants is still your activation energy. But as always, the difference between your products and your reactants is still delta H. But in this case, in our endothermic reaction, since our delta H is positive, our products have more energy than our reactants. And that's how the potential energy changes over time as you have an endothermic or an exothermic reaction. Okay, let's talk about Hess's law. Hess's law is going to allow us to manipulate these reactions and their enthalpy values, and it has like three different things that we can talk about Hess's law. So Hess's law starts with if you have a reaction that's A plus B yields C, and its enthalpy value is plus 50 kilojoules per mole. If you flip the reactions, if you make C the reactants and A and B the products, your enthalpy changes to negative 50. So the sign flips. The second thing is if you have A plus B yields C, and that's enthalpy value is 50, if you wanted twice of that, twice of everything, you would also multiply the enthalpy value by whatever you multiplied by. So in this case, 2. And the last bit tells us that if A plus B yields C and C yields D plus F, then we can add up the reactions and also add up the enthalpy values to get the enthalpy change of the total reaction. That's the three postulates of Hess's law, and let's see how it's used in a problem. So given the enthalpy changes, A plus B yields C, that has an enthalpy change of negative 35 kilojoules per mole. A plus D yields E plus F, enthalpy of plus 20. F yields C plus E, enthalpy of plus 15. What is the change in enthalpy for the reaction 2A plus B plus D yields 2F? Okay, we need to find a combination of these three reactions that's going to yield our final reaction that we want. So we want 2A plus B plus D yields 2F. Now, if you notice, the only reaction that has a B in it is our first reaction. Since that B is on the reactant side, we know that we're going to need one of the first reaction. So we know that what we have so far is A plus B yields C. So now we need one more A. The only source of A that we have that we can get is from the second reaction, so we know that we need one more of that. So we have A plus D yields E plus F. And if you add these two blue ones up, you get 2A plus B plus D yields C plus E plus F. That's pretty close to our top expression here. But the thing we need to do is we need to involve our last equation here. The way you incorporate it is you take the negative of it. So instead of taking the reaction as it is, you flip it. You do C plus E yields F, and that has an enthalpy change of negative 15. So we can do C plus E yields F, and if you add all these up, these cancel, and you get 2A plus B plus D yields 2F. And so we had one of the first one of the second one, and negative one of the third one. So if you add these up, that's negative 35 plus 20, and then negative 15. And that comes out to negative 30 kilojoules per mole. And that's answer choice B, and that is the right answer. Okay, let's talk about the other types of enthalpy. One of them is the enthalpy of formation, the enthalpy of formation. The enthalpy of formation is the change in enthalpy that occurs when 1 mole of a substance is formed from its component pure elements under standard state conditions. So it's also sometimes called the standard enthalpy of formation, or just the heat of formation. So you might be wondering what standard state conditions are. Standard state conditions depend for what you're talking about. For gases, it's just 1 atmosphere of pressure. For liquids and solids, it's going to be the most common and stable form of the compound at 1 atmosphere and 25 degrees Celsius. And for solutions, it's going to be 1 molar concentrations. For example, for solids, you would use graphite instead of diamond because graphite is far more common than diamond. Alright, now that we know the conditions, let's talk about how the value changes based on what you're dealing with. So for example, if you were a pure element in your standard state, your enthalpy of formation would just be 0. And this includes your diatomic elements like oxygen and like iodine and stuff like that. For a pure element not in a standard state, your enthalpy of formation is not 0. So carbon in its graphite form would have a enthalpy of formation of 0, but carbon in its diamond form would not have an enthalpy of formation of 0. As you can see, it's 1.88 kilojoules per mole. For compounds, you have to look at the entire reaction in order to find that out, and we're going to be able to calculate that. So it's going to be the enthalpy of the products minus the enthalpy of the reactants. So if you have this little expression here, let's work through the math here. So we have 2 carbon dioxides in the products. So 2 times negative 394 kilojoules per mole, and then that's added to 4 times our water. Water is negative 242 kilojoules per mole. And then you take all that and you subtract it from your reactants. So your reactants is 2CH3OH, 2 times negative 201 kilojoules per mole, plus 3 oxygen. So 3 times 0 kilojoules per mole. It's 0 because the enthalpy of formation of a pure element in its normal form is 0. And if you work through all the math, that is going to come out to negative 1,354 kilojoules per mole. And that's how you calculate the enthalpy of formation of that's how you calculate the enthalpy of reaction using your enthalpy of formations. And that's the right answer. One more thing about the enthalpy of formation that I want to mention is that when it comes to the enthalpy of formation of a product, or of a compound, you always want a chemical reaction where only one molecule of your product is being formed. For example, if you look at our expression here, you'll see that only one molecule of carbon dioxide is being produced. And it's the same with the CH3OH here too. You can see that there's a stoichiometric coefficient of 1/2 on the oxygen, and that's just there so that we can have only one molecule of our product being formed. And that's enthalpy of formation. The next type of enthalpy that I want to talk about is called bond enthalpies. The idea behind bond enthalpies is that bonds store energy. When you form a bond, energy is released, and when you break a bond, energy is absorbed. And that might seem counterintuitive. You might think when you break a bond, energy is released. But the thing is, in the context of the system, when you go to break a bond, you need to add energy into that system. A bond's not just going to break on its own. You're going to need to add some sort of energy to that system, and that energy is absorbed, and that energy is used to break the bond. And it's the opposite for forming a bond. When you form a bond, energy is released. And you have a diagram, a table of a couple average bond enthalpies of different bonds. You can see that multiple bonds are stronger than single bonds, like a triple bonded carbon-carbon is much stronger than a single bonded carbon-carbon. And the thing with bond enthalpies is that you can use them to measure the enthalpy of a reaction. So the enthalpy of a reaction is the sum of the bond energies of the bonds formed plus the bond energies of the bonds, it's the bond energies of the bonds broken plus the bond energies of the bonds formed. The thing about this is that the first value is going to be a positive value, but the second value is going to be a negative value. This goes back to the fact that when bonds are broken, you absorb energy, and when bonds are formed, you have less energy. Energy is given away. So when you go to break one of these bonds, you're going to get the positive value of this average bond enthalpy. If I went to go break a CH bond, I would need to put in plus 413 kilojoules per mole of energy. But if I went to go form this CH bond, I would lose 413 kilojoules of energy. I would get that from the system. So you have to change your value into a positive or a negative value based on whether or not you're forming the bond or you're breaking it. So you can calculate the enthalpy of reaction by summing up the bonds broken and the bonds formed but remember that the bonds formed are a negative value. So let's do a problem here. Given the bond dissociation enthalpies below, what is the approximate enthalpy of formation for H2O gas? Alright, since we're talking about the enthalpy of formation, we know that our reaction, the reaction that we want to find the enthalpy of, is going to involve creating one molecule of water at the end from its component elements. And the component elements are hydrogen and oxygen. And both of these are diatomic, so you're going to see H2 and O2. This isn't currently balanced. In order to balance it while keeping a coefficient of 1 in front of our product, you need a coefficient of 1/2 in the oxygen. Now from here, remember our enthalpy of reaction is just going to be the bonds broken plus the bonds formed. So let's see what are going to be the bonds broken. The bonds broken is going to be 1 of this HH bond and 1/2 of this oxygen bond. A oxygen bond in O2 is actually a double bonded oxygen. So our value comes out to 1 times 432 kilojoules per mole plus 1/2 times this double bonded oxygen, which is 495 kilojoules per mole. And it's added to the bonds formed. And the bonds formed are going to have a negative value. So while we're adding it, we're really going to be subtracting those values. So we have water, we have H2O. H2O is going to look like this. So it's just 2 of these OH bonds. So 2 times negative 467. Since you're forming those bonds, energy is going to be released. Kilojoules per mole. And if you go to add this all up, this comes out to negative 255 kilojoules per mole, which is answer choice D, and that is the right answer. There are a couple other enthalpies. These enthalpies deal with the enthalpy of a phase change. So the enthalpy of fusion is going to be the energy change required to change 1 mole of a substance between solid and liquid states. Enthalpy of vaporization is from liquid to gas states, and enthalpy of sublimation is from solid to gas states. The enthalpy of vaporization is going to be somewhat helpful. We actually know the relationship between the temperature of a liquid and its vapor pressure. The relationship between it can be told if you know your enthalpy of vaporization. So liquids are going to have different vapor pressures based on what temperature you're at, and the relationship can be portrayed if you know your enthalpy of vaporization. The relationship is expressed in the form of the Clausius-Clapeyron equation, and it tells you that the natural log of pressure 2 over pressure 1 is the negative enthalpy of vaporization over R times 1 over temperature 2 minus T1. The big thing is that your enthalpy of vaporization is in joules per mole. Sometimes your enthalpy value is given in kilojoules, so you have to make sure to convert kilojoules to joules. And R, in the context of this problem, our units need to be joules over mole times Kelvin, so our value is 8.3145. Let's do a problem. What is the boiling point of water in a pressure cooker with a pressure of 2 atmosphere, and the enthalpy of vaporization of water is 40.7 kilojoules per mole? Since we have our enthalpy of vaporization and we're dealing with different pressures and different temperatures, you know that you're going to be using the Clausius-Clapeyron equation. And remember, the equation goes the natural log of pressure 2 over pressure 1 is equal to the negative enthalpy of vaporization over R times 1 over temperature 2 minus temperature 1. Let's say our temperature and pressure 1, so P1 and temperature 1, is going to be the normal boiling point of water. The normal boiling point of water is at 1 atmosphere, and it tells you that it boils at 100 degrees Celsius. 100 degrees Celsius is 373 Kelvin, and you want to use Kelvin for your temperatures. Be careful about that. So that's temperature 1 and pressure 1. Let's do pressure 2 and temperature 2. Now, the thing with pressure 2 and temperature 2 is that we know our pressure. We know that's going to be at 2 atmospheres, but the question tells us to find the temperature at which you have this gas, at which you have this boiling point. The last thing that we know is our enthalpy of vaporization. We know that our enthalpy of vaporization is 40.7 kilojoules per mole. So let's write that in joules per mole, since that's what we're going to be needing to use. And now we have all the information that we need in order to solve this problem. So we know that the natural log of pressure 2, that's 2 atmospheres, over pressure 1 atmosphere, is going to be negative 40,700 joules per mole over 8.3145 joules per mole times Kelvin. And then it's going to be 1 over temperature 2. We don't know temperature 2. Temperature 2 is what we're trying to find at the end. Minus 1 over temperature 1. Temperature 1 is 373 degrees Kelvin. And if you solve for temperature 2 is going to come out to about 394 Kelvin. And 394 Kelvin, you can convert that to Celsius by subtracting 273 Kelvin, and that comes out to 121 degrees Celsius, which is answer choice B. And that is the right answer. So that's how you use the Clausius-Clapeyron equation, as long as you know your enthalpy of vaporization, to see how the vapor pressure of a liquid changes as you change the temperature. And that's all I have for enthalpies. I hope you were able to learn something. I hope this video was helpful, and I hope to see you later. Thank you for watching.